Today we're going to perform something called rationalizing the denominator. So right now you can see that on all of these problems, the denominator is irrational. That means that we cannot come up with a fraction to represent the answer. So with that said, we would have to approximate the divisor in order to do the division. And so we don't come up with as accurate of an approximation when we do that. So that's why we do this thing called rationalizing the denominator. So we want this in a simplified form, and that's when we have the denominator as a fraction or any kind of whole number or number that is rational. So what we're going to end up doing to get a rationalized denominator is to multiply this by a square root that'll make it a perfect square. And so the easiest one to do is multiply it by the number that we already have there, the 7. And so 7 times 7 makes 49. So up on top, we have 6 times the square root of 7, but down below we have the square root of 49, because again, as I said before, 7 times 7 is 49. Now you can see that when we go ahead and simplify this, we're left with 6 square roots of 7 over 7, and this is an equivalent fraction to the one in black that we had originally started with, but now we have a rationalized denominator. 7 is a rational number. And it makes the approximation a little bit easier to deal with, because now we have to divide 7 into this product. On this next one, same sort of thing. You're going to multiply by a number that will cancel out the 14, the square root of 14. So you see, if we multiply by the square root of 14 over the square root of 14, this number that we came up with here is just 1. And so again, 1 times the number doesn't change the value, it just changes the appearance. And so what we'll do is multiply across. 4 square roots of 14 is what I have on top. Down below, 14 times 14 makes 196. And so from that point, we can go ahead and take the square root of 196, and that gives us 14. Well, we can still do some reducing. Can't reduce the numbers inside the radical with numbers outside, but I can reduce the 4 and the 14. So you see how 2 goes into each of these numbers. So that's what I just divided by there. So now I have my answer, 2 square roots of 14 all over 7. That is our answer. Well, taking a look at the next one, same sort of thing. Square root of 6 over the square root of 6 is just 1. 1 times the number doesn't change the value of the number, just changes it to an equivalent fraction. So now I've got 8 square roots of 6 all over the square root of 36. So I'll go ahead and take that square root of 36. So now I've got 8 square roots of 6 over 6. Well, I have the same situation as the last one. I can reduce the fraction. Take out the common factor of 2, and we've got ourselves a simplified expression. 4 square roots of 6 all over 3. Well, same sort of thing on the next one here. We need to rationalize this denominator, so I'm just going to multiply by the square root of 7 over the square root of 7. So difference here is that on top now we have a radical. So when we're multiplying a radical by a radical, we can multiply the numbers underneath the radical sign. So I can do 7 times by 15, multiply those two numbers. So when I do that, I get 105. And there's no perfect squares in 105. 7 and 15 don't have any common factors, so no perfect squares there. But down below we have 49. And so we can take that square root of 49, and that just makes 7. So 3 times the square root of 105 all over 7. Well, the next one's a little different. Actually, the next 4 are all different. See, typically we've been just multiplying by whatever the denominator is. However, in this case, we can do some reducing, and that's what I'm going to do here. One of the rules with radicals is that if you have a common index, which we do, the square root, you don't see the little index number here, so we take this as a square root. So what I'm going to end up doing is I'm going to go ahead and do some reducing. And so I'll go ahead and divide the number, the common factor here. So I'm going to take out a 2 in each of these numbers. So you see I can take out a 2, this becomes a 4, and this becomes a 7. So now I've just made the problem a little bit easier. So now I have 2 square roots of 7 all over the square root of 4. Well, the square root of 4, well, that's just 2. So now I have 2 square roots of 7 all over 2. And I can reduce this by taking out these two 2's. So all I'm left with is the square root of 7. That is the answer. So in this one, we can't do any reducing like we did on the last one because there's no common factors. But we can take out a common factor that's a perfect square of 12. You see, 12 we can break down to 4 times 3, and 4 is a perfect square. So let me rewrite this like that. The square root of 3, or 3 square roots of 5, over the square root of 4 times the square root of 3. See, the square root of 4 is 2, so now I've got 3 square roots of 5 all over 2 square roots of 3. Well, all I have to do then to rationalize the denominator is multiply by the square root of 3. See, it's a smaller number, so it's easier to multiply by. And so I can go ahead and do that multiplication. And again, you can multiply the two numbers underneath the radical sign here, since they're both underneath the same type. So now I have 3 square roots of 15 all over 6. I got 6 because the square root of 3 times the square root of 3 is 9. See, again, these two numbers right here, those multiply to make the square root of 9. The square root of 9 is equal to 3. 3 times 2 made 6. So that's where I got those numbers. However, we're able to reduce a little bit now. You see how 3 and 6 have a common factor. So we can reduce that down. Now I've got the square root of 15 all over 2 as my answer. Well, taking a look at our next one, same sort of thing. Look always for the perfect square as a factor of the number. See, we have the square root of 9 in the square root of 6. The square root of 9 is 3, so we could rewrite this as 2 square roots of 7 over 3 square roots of 6. And so we can go ahead and multiply by that factor, or by that number that makes a perfect square. Square root of 6 over the square root of 6. So now we've got 2 square roots of 42 all over, and then the square root of 6 times the square root of 6 makes 36. The square root of 36, which just makes 6. So now we have 2 square roots of 42 over 3 times by 6. Well, we can reduce that a little bit. You see the 2 up on top and the 6 down below have a common factor of 2. So do that division, and we've got this as our answer. The square root of 42 all over 9. Well, where did I get 9? Well, it's the 3 and the 3 that I multiplied together when I reduce the 6 and the 2. Left with 3. 3 times 3 makes 9. Well, the last problem here is similar to those others, where there's a common factor, where there's a factor in 50, and it's a perfect square. See, 25 times by 2 makes 50. Always look for the perfect squares. 5 and 10 make 50, but those don't help me out, because those are not perfect squares, but 25 is, so that's why I use that number. So now this makes just 5, so 5 square roots of 2 is what my denominator is going to be. So I've got 9 square roots of 11 over 5 square roots of 2. So now let's go ahead and multiply by a number that's going to cancel out that denominator that makes it a perfect square. And so that's going to be the square root of 2 over the square root of 2. So now I've got this. I've got 9 square roots of 22 all over 5 times by the square root of 4. Well, the square root of 4 is just 2. So now I've got this. 9 square roots of 22 all over 5 times 2. Well, no common factors. Can't reduce the 22 and the 2 because the 22 is underneath the radical sign. So this is all I can do. 9 square roots of 22 all over 10. And that's the answer I'm looking for. Well, those are similar problems to what you'll see on tonight's homework. Good luck.